Welcome back, folks. Last component to look at to figure out the impedance, the complex relationship between voltage and current. This one's going to be for the inductor. So we're playing the same game. The math changes ever so slightly because the inductor equation is different than the capacitor equation. So let's get at it and see what we're doing here. Okay, so we take that same sinusoidal voltage source and we put it across an inductor this time. Okay, and we're interested in finding this current through that inductor if we put this voltage across, just like that. All right, so our voltage, as it was before, is A cosine omega t, why am I doing that? Omega t plus theta. Okay, and that's of course in volts. Now if we want to find the current through an inductor, we have to use the integral form. Okay, and that's what makes this one a little different. 1 over L. Okay, and we're going to take the integral of V, and being careful with our variables of integration, t and d tau. We're going to use tau. All right, so taking that integral, the integral of the voltage, let's see, the integral of the voltage, let's get the integral of the voltage, there we go, A cosine omega t plus theta dt. Okay, well, now we're taking the integral of a cosine, so that's going to be a sine, and A is a constant, so that's going to pop out, right? So if I'm working this over here, we can say A pops out. We have the sine omega t plus theta. Okay, but we also have to remember U substitution. And because of U substitution, we're going to have another omega pop out. It's going to pop out in the denominator. Okay, if I derive that, I should get back to the voltage, right? So if I derive a sine, I get a cosine, and it's going to have all the same stuff inside. And the omega is going to pop out because of the chain rule, but it's going to pop out in the numerator, so that will cancel there. And A is a constant, so it's just kind of along for the ride. So that integral looks good to me. Hopefully it looks good to you too. Okay, so moving over here, we get I of t is equal to 1 over L. Okay, so really we just need to add that 1 over L. So 1 over L times the integral of the voltage. So 1 over omega L sine omega t plus theta. And now that's in amps. Okay, so we have the voltage, we have the current, we know what to do from here, right? We say the impedance of the inductor is equal to the voltage over the current. Okay, and since we are lazy, and since we've done years of damage from typing and spending way too much time in college, we can get the voltage here, okay, and we can divide by the current, and then we play the same kind of game where we reduce this down as much as we can. We have a cosine and we have a sine again, right? So we have A, and this one's going to turn into 1 at an angle of theta using our phasor transformation. Just looking at this, right? So that comes down there. All of that is over, well, we got to take our sine and we've got to rewrite it as a cosine, but we know how to do that as well, right? So this is going to become cosine omega t plus theta minus 90 degrees. Okay, and we're going to bring that down. A over omega L stays right where it is, and we bring this down as a phasor. It is 1 theta minus 90 degrees. Okay, very similar to the capacitor. Okie dokie, ready? We know how to do that division. We get, well, let's get rid of A, right? A is just pesky and kind of in the way. That's going to drop out, and that's going to drop out. 1 over omega L is going to turn into omega L. Okay, and then we're going to have this phasor division is going to be 1 over 1 at an angle of theta minus theta. Ooh, don't lose that bracket because we got to distribute that negative sign. Okay, it's going to look like that. So we're left with the impedance of the inductor is omega L times 1 at an angle of, well, theta minus theta is 0, and then minus a negative 90 is a positive 90. Okay, from the last video, 1 at an angle of positive 90 is also known as J, right? So this is just J. This is the polar form, this is the rectangular form. So Z over L is equal to, and the way you're going to see this one written most of the time is J omega L. Okay, that's the payoff on this one. That's the impedance. We have a complex relationship for the voltage as a phasor and the current as a phasor. Okay, so let's put this all together. I promised you I'd do it in this video. So we've got 3 passive components. We've got the resistor, we've got the capacitor, and we've got the inductor. We've got a handful of values that we're interested in. For the resistor, we're interested in the resistance, okay, which also ends up being the real component. Did you notice that the impedances of the capacitor and the inductor were purely imaginary? So we have this other value that we talk about. We talk about the reactance. Okay, so this is the reactance, which is just the imaginary component of the reactance of the impedance. Okay, and then we can put those together into the impedance. So the resistor was purely real, and the resistance was R. So maybe this wasn't, maybe I should write out the word. Okay, for the resistor, the resistance was R, and the reactance was 0, and then we can put that together, and this kind of feels silly, but we can put that together into the impedance, R plus J0. Okay, for the capacitor, there was no resistance. For an ideal capacitor, there is no resistance. There is no real component. For the reactance, we have negative 1 over omega C. Okay, it's the magnitude of the imaginary component. And then we can put them together as 0 minus J over omega C, where the other form you're going to see that in is 0 plus 1 over J omega C, and then the 0 usually gets dropped in that form. Okay, they're equivalent. Invert negative J and you get positive J. Okay, last one, the inductor. There is no resistance, and the reactance is omega L, and we can put that together, and we can say 0 plus J omega L. Okay, so out of all of this, this table, I gotta not cut off my hands. This table is kind of the important thing. It's what we're going to use when we start to move circuits out of the time domain and into the phasor domain. We're going to have to relate the voltages and currents, and we're going to relate the voltages and currents using this table. Okay, so this is going to get stuck in your head, I promise you. There's going to be enough repetition to make it stick. Okay, a little bit more on impedances because we can combine them. That's what's coming up next. And then we'll start to use this stuff to do circuit analysis. That's what I really want to get to, but I want you to understand where it comes from. Ohm's law, KVL, and KCL. we're forcing Ohm's law to be true and become super Ohm's law. Okay? So equivalent impedance is next, and then circuit analysis, I promise you. Stay tuned and good luck.